You know, electrical circuits can often look like an impossibly tangled puzzle, right? Just a mess of wires, resistors, and power sources that seems completely intimidating. But what if I told you there's a secret toolkit? A set of elegant, powerful, and honestly, surprisingly simple rules that can let you solve even the most complex circuits out there. Well, today, we're opening that toolkit.
All right, just take a look at this thing. We've got voltage sources, a bunch of resistors, and there's even a dependent source in there. That's one of those tricky components whose output is controlled by something happening somewhere else in the circuit. It's all just connected. So where would you even start? How in the world do you figure out the current flowing through that 120 ohm resistor right in the middle? I mean, trying to solve this piece by piece would be an absolute nightmare, but with the right tools, it actually becomes a pretty straightforward process.
So to solve a beast like that, we have to start with a solid foundation. And that foundation was laid down for us way back in 1845 by a German physicist named Gustav Kirchhoff. He gave us two unbreakable laws that are the basis for pretty much all of circuit analysis. These are our first and most important tools in the kit.
And what's really cool is how these two laws create this perfect balance. First, you have Kirchhoff's current law, or KCL. This one's all about the junctions, or nodes where wires meet. And it's simple. The total current flowing into a junction has to equal the total current flowing out. Just think of it like water in pipes. What goes in must come out, period. Then, on the other hand, you have Kirchhoff's voltage law, or KVL. This one applies to any closed loop in a circuit. It says that if you take a walk around any loop, adding and subtracting all the voltage changes, you have to end up at zero. You always get back to where you started.
Okay, so with those two golden rules in our back pocket, now we can build some more powerful systematic strategies. See, instead of just applying the rules kind of randomly and hoping for the best, we can use these really organized methods to solve complex circuits super efficiently. And they build directly on KCL and KVL.
First up is nodal analysis. This method basically takes Kirchhoff's current law and just applies it very systematically to every important connection point or node in the circuit. The entire goal here is to figure out the voltage at each of these nodes, because once you know all the node voltages, you can find pretty much anything else you need to know. Now, the natural counterpart to nodal analysis is something called mesh analysis. If nodal was all about KCL and nodes, you can probably guess that mesh is all about KVL and loops. With this method, we define a current for each little window pane or mesh in the circuit. By applying Kirchhoff's voltage law to each one of those loops, we can solve for all the mesh currents directly. And this right here, this is the core idea. It's the secret sauce. These powerful techniques, they aren't some brand new, complicated physics. They're just really organized, really clever applications of our foundational rules. Nodal analysis is just a smart way of combining KCL with good old Ohm's law. And mesh analysis, it's the exact same idea but with KVL and Ohm's law. It's just an elegant system that's built from really simple parts.
But let's be honest, what if you don't care about every single voltage and current in some massive circuit? What if you only care about what's happening at one specific part? Well, for that, we have a true power-up, an incredible shortcut. It's called Thevenin's theorem.
This is what makes Thevenin's theorem so unbelievably useful. You can take a huge, complicated part of a circuit. It doesn't matter how many sources and resistors it has, and you can replace all of it with this incredibly simple equivalent circuit. We're talking a single voltage source in series with a single resistor. That's it. It just completely demolishes the complexity.
And the process is surprisingly straightforward. First, you take out the component you care about and find the voltage across the open terminals. That's your V-Thevenin. Second, you turn off all the independent power sources and calculate the total resistance you see looking back into those terminals. That's your R-Thevenin. And finally, you just reconnect your component to this brand new, super simple circuit and solve. It is an absolute game changer.
So let's recap. We have our foundational laws, KCL and KVL. We've got our systematic strategies, nodal and mesh, and we have our amazing shortcut, Thevenin's theorem. But there's one final, really beautiful secret that's been hiding underneath it all, a hidden symmetry that connects every single tool we've just talked about.
I mean, think about it for a second. Have you noticed the pattern? We had a law for current at a node and a law for voltage in a loop. We had an analysis method based on nodes and a method based on loops. It's like this perfect mirror image relationship, right? Well, let me tell you, that pattern is absolutely not a coincidence.
This powerful principle is called duality.
It's a really fundamental concept in circuit theory. What it means is that for a whole bunch of rules and relationships, you can find a perfect dual by just swapping a few keywords: voltage for current, series for parallel, loop for node. And the amazing part is, the new statement you get is just as true as the original one.
And here it is, the whole beautiful symmetry, all laid out. Voltage is dual, current. A series circuit's dual is a parallel circuit. KVL, our loop law, has its perfect partner in KCL, our node law. Mesh analysis has its twin in nodal analysis. And yep, even our superstar Thevenin's theorem has a dual. It's called Norton's theorem. Instead of a voltage source and series resistor, it simplifies a circuit down to a current source and a parallel resistor. Everything has a perfect partner.
And listen, this isn't just some clever mathematical trick to make exams easier. This symmetry, this duality, it comes from the deep physical relationship between electricity and magnetism themselves. The patterns we're seeing in these circuit analysis tools are literally a direct reflection of the fundamental laws of our universe. How cool is that? You know, when you realize that this elegant, hidden structure exists in something as practical as circuit analysis, it's a pretty powerful idea. This principle of finding duals and symmetries pops up in so many other areas of physics and mathematics, and it really makes you wonder, right? It just begs the question, what other incredible unifying patterns are just out there waiting to be discovered in the world all around us?